But yes, it is very true, and this talk is a great example of it. So it's a small enough room. This talk kind of builds as it goes. So if there's any point you have a question, just shoot your hand up, and we'll take it and deal with it before moving on. So, and also I'm very relaxed, so don't feel like you have to hold back or anything. But let's get going. All right, the best we can do. How good can we do programming? I'm talking about the higher order virtual machine. I saw this guy tweet about this a little over a year ago, and he talked about an exponential speedup over Haskell for some programs. And I am a complete sucker for exponential speedups. So I bought the book, spent 6 months on the first 2 chapters, and know very little. But we're going to start where all good talks start with, is Lambda Calculus. For those of you that aren't familiar with it, this is a quick example of the syntax. A lambda expression starts with a lambda. There's a variable, or a parameter, which is usually a single character, a dot, and then the body of the expression. In this case, the body is an application between 2 parentheses, and the left variable, the y, is the free variable because it's nowhere defined. The x is a variable or a bound variable that will be bound to the parameter. And we'll cover what all those mean. So basically in Lambda Calculus, you have lambda expressions like this, single variables, and applications. And that's it. So an application, in this case, the lambda expression is being applied to z. So z is a free variable, and so you just replace the parameter in the body of the lambda expression with whatever the argument is. So the lambda expression becomes just yz. Everybody see that? Okay, so key points. The Lambda calculus can compute anything. It is a universal computation language, system, whatever. Haskell Curry kind of introduced it in the 30s to try to formalize logic. It eventually became the tool to study programming languages. But it can compute anything. Even though there are no numbers and stuff, you can do all kinds of crazy things and compute anything with it. So here's an example, quickly. We have 2 expressions. One is a lambda expression on the left being applied to a lambda expression on the right. So let's start with that lambda expression on the right. Inside of it, it's the lambda q expression, which is being applied to the application expression yz. So yz gets doubled, or gets duplicated, and put into both slots where the q is. Simple substitution. And then you do the same thing. You take the whole lambda y expression and drop it into the lambda body of the lambda x expression for x, and you get that. And then you take the lambda w expression and drop it into the lambda y expression, and you get that step. And then you, in the left-hand expression, you just apply the z into the w, and you get z, because the lambda w dot w is just the identity expression. And then you do the same thing for the other side, and you get this form. So the entire point of a lambda expression is to boil it down to the simplest, smallest expression you can get it, so that there's no more applications to be done in it. This is called the normal form. So that bottom expression is the normal form of the top expression. And there's no more work to be done on that bottom expression. Okay. So let's look at this expression again. You'll notice that back then, there were 5 steps. It took 5 steps to get to its normal form. So let's look at this same expression, except we'll make some different choices. In this case, we're going to take the entire lambda y expression and drop it into the lambda x. And then we take the lambda WW expression and drop it into for the y. And then we drop the whole lambda WZ expression in and drop it in for the Q. Lost track. Drop the Z in for the W and get just Z back. And then drop Z into the lambda Q expression. And we get the same normal form as we got before. However, notice that there are only 4 steps in this path. That is the key to the whole talk. One of them is there is an optimal way to reduce a lambda expression to its normal form. However, there is no algorithm to always optimally evaluate a lambda expression to its normal form. And this kind of breaks down, you can think of it as the difference between lazy and strict. In like C or Java or whatever are strict and Haskell is lazy. No matter which option you choose, you are in some expression, some algorithm, some program, you're going to be doing work that's unnecessary. So there is no optimal evaluation algorithm for the lambda calculus. Okay. Everybody with me? All right. Here's another lambda expression. Or actually, it's the same one. So if you take that lambda expression, you can rewrite it as a tree. And I'm using the @ sign for application instead of the parentheses. So everybody there? Because now we're about to make the jump to the core of the talk. So if you take this tree, it's literally a tree, and all of the variables are just where the edges will connect. So you can eliminate the variables and just replace them with edges that connect from one location to the other where the variable appears. And then you move from that tree to this graph. And it is clearly a graph. It is not a DAG because there are cycles. The edges are not directional. It's a graph, okay? Okay, so any lambda calculus expression that you get as text can be drawn as a graph. So now we get to the fun stuff. This is stuff that blew my mind. I had no idea this even existed. This is a completely new, not relatively, I mean, yeah, depending on your definition of new, but a completely different model of computation than I ever knew about. And when I started looking at it, I was like, I didn't even know you could do that. So here we go. Here's the graph. Now, you'll notice on the left that there are dots at the ends of edges. Every node, and there are really only 3, the lambdas, the applications, and this triangle, which is a duplication node. And we'll talk about that here in a second. They all have a dot for one of their ports where an edge comes into it. That is the principal port of that type of node. Anytime you have 2 principal ports connected by an edge, like up there at the very top left, that means you can apply one of these combinators, one of these operations on the right-hand side, and reduce the graph. Okay, is everybody there? Cool. So like in the upper left, if you have those 2 nodes, that would be this combinator right in the middle. So you take out the application node, you take out the lambda node, and you connect the edges, or the nodes that are at the ends of the edges. So it reduces the graph. Now, in some cases, like over there at the far right, bottom right, you actually expand the graph. You add some nodes to it. So it's not strictly shrinking the graph all the time, but it is reducing the graph. And you'll see about all that in a second. So all of this is beautiful except for these 2 combinators down here at the bottom right. You'll notice they start with the same configuration, and then they go to 2 different ones. The whole problem of interaction combinators is how do you decide which one to choose? It's like recursion in Turing machines or whatever. It's the fly in the ointment. Everything else is just beautiful and simple and easy. It's that decision, how to make that. So, and I'm just going to wave my hands and say we just know, because I don't have time to explain it. And frankly, I don't understand all of it myself. All right, let's look at this lambda expression. It produces this graph. So let's start reducing it. Let's choose that top from at 1 to lambda 1. And we'll apply this combinator. And then the graph looks like this. Everybody see that step? Okay. So then we take that graph, and what are we going to do next? We're going to do another application of the lambda. I think that's app 3 to lambda 4. And so you remove those nodes, connect the edges, you get that graph on the right. Then you start at that graph. And now we're going to duplicate the lambda. And by the way, lambdas are analogous to functions. So in this case, we're duplicating a function. And when you do that, you get lambda 4 and lambda 5 get introduced over there. But notice that the body of the lambda is not duplicated. That duplication node, that triangle, just moves through the lambda nodes and duplicates them, but they're sharing the body. That's a key point. So we take that graph. We're going to apply another application. And there we go. We applied application 2 to lambda 4 and to get the graph on the right. So when you're working with the HVM and the stuff, you look at these graphs all the time. Your eyes go cross-eyed. But it's just what you do. So take that graph. Now we are going to duplicate an application node. So you'll see the triangle, the duplication node, moves through the at node, duplicates it, and then produces this. So now we dropped at 4, and we have at 6 and at 7 now. So now we have that graph. We're going to duplicate a lambda again. And we move to that graph. So we're just choosing these 5 operations, just repeatedly, over and over again. But you can see the graph is sometimes gets a little bit more complicated, but it's kind of moving toward a similar form. So now we're going to do an annihilation of 2 duplication nodes down here on the bottom. And so the body of this lambda, which is just the identity, was shared, but then it becomes duplicated. Now we have 2 separate identity functions. Then we're going to duplicate 2 nodes. This is the 2 in the middle. And so the graph then looks like this. So then we have the graph there. We're going to apply a lambda. And the graph then becomes that. So this is maybe a little bit harder to see, but we applied lambda 5 and application 6. They're at 2 different places, but they have that big edge that connects them. So they get eliminated. And then, by the way, this line that goes out to the top, that's where the result is going to go eventually. That's just where the result is. So now we start here. We're going to duplicate an application. So we're up here duplicating application 5. and we get 8 and 9. And yeah. So then we do there. And now we're going to annihilate a pair of duplications. And it becomes simpler. And then we take that graph, we duplicate or annihilate. Yeah, top, there it is. Geez. Like I say, especially when you're like, oh crap, I messed up my slides. And they're like, oh man, the rest of the talk is ruined. We're toast. Okay, so then it's there. And I mean, from here, it's just pretty straightforward. You apply a lambda to at application 7 to 6, and then that gives you just lambda 7, which then gets duplicated, which then you apply 9 to 8, and that becomes simpler, and then lambda 9 gets duplicated. And then you apply 8 to 10, which just gives you lambda 11, the identity. So this graph, normal form, is just the identity expression. And we did it strictly using graph reductions, the 5 combinators. Everybody there? Okay. Exactly. I mean, you do. You have to just sit there and look at the graphs, and it just takes practice. But the idea, hopefully, is there. So any lambda expression can be drawn as a graph. However, not every graph that we saw could be written back into a lambda expression, a textual lambda expression. Like when you have 2 lambda nodes sharing a body, there's no way to really write that in text. So that's a key point. I mean, that's why the slide is called key points, is that if you're doing the graph reductions, it can go places that a simple text substitution algorithm can't go. The other thing, and this is what was really mind-boggling, is you'll notice that any graph can have any number of pairs that are connected that can be reduced at any time. So you can choose to do those in any order, or you can choose to do those all in parallel, do them all at once, because they're only local to that part of the graph, those 2 nodes. And so, and then lambda expressions can share the same body. So if 2 lambda expressions share the same body, then that body can be optimized, can be reduced and optimized before either of them get applied. And so they're both optimized in one operation. So you're not going through, you're not doing like peephole optimization or program transformations or whatever. It's just simply reducing the graph.
It's almost like normalization for graph operations.
If you say so. So yeah, and I mean, actually, that's a good point. I began my career doing control systems for sewer plants. I got my degree at a university that was comp sci, but very engineering oriented. So I missed out on tons of math. So when something like this comes along, I'm like amazed and totally perplexed. I have no idea what they're talking about, but it's cool. The higher order virtual machine is literally an implementation of what I just showed you. You take a high-level language, you compile it like Python or Elm. They have plans to do this. Compile it to what's called HVML. It's kind of a low-level, still text, but low-level description. And then the HVML compiler turns that into a graph data structure. So in memory, it's literally a bunch of addresses that is a data structure. So your entire program becomes a graph data structure. And then there's a kernel written in Rust that applies these graph operations on it continually. And it handles things like deciding which of the two operations to use, and it reduces the graph. And it runs it in parallel. And it does it on GPUs using CUDA. Oh, by the way, the release of version 1 or whatever is like in 10 days. It's supposed to happen in 10 days. And Victor, the guy who's mainly doing this work, posts on Twitter. And I'll give you his Twitter handle. Just amazing updates. It's mind-boggling. He got it up to 73 billion of those graph operations per second on his NVIDIA graphics card. 4096, 4092, something. 73 billion graph operations.
Is that on the same graph? Or?
On the same graph. Yeah. It's
okay.
Okay, now here's the part that leaves my jaw dropping. The implications of this. There are no needs, there are no threads. There's no async. There's no concurrency. Any part of your program that can be done in parallel gets discovered automatically. So you write single-threaded code, what looks like single-threaded code, and it will find the parallelism, and it will do it. And there's no notations. You don't have to say, this is whatever, whatever. There's no deadlock. There's no semaphores, no mutexes. None of the garbage of async stuff or threads, concurrency, none of that is needed. The graph just gets reduced. And it all happens automatically. Your cores stay going as much as possible, and it just cranks along. Yeah?
Lambda calculus, an expression has a reducible expression that does not terminate. Normal order will find it, but non-normal order is not guaranteed to find it. How does that manifest in the system you've outlined?
I have no idea what you're talking about. No, seriously. I don't know. What I can speak of from a mechanical system is it just keeps chewing away on the graph, and it'll reduce a pair, and if that reduction generates more pairs to reduce, it puts those onto a list to be reduced later and a queue, and it'll just keep chewing these pairs that need to be reduced repeatedly, and it may or may not terminate, but it'll just keep chucking along. And by the way, you can extend the Lambda calculus. I mean, they add integers to it, they add types, they add all kinds of stuff. And so you can extend the Lambda calculus to do I/O, have special functions that do I/O and stuff. So that's kind of what this virtual machine does. And so it'll call your I/O functions and spit out I/O forever. So optimizations happen automatically. Are you guys familiar with the term map fusion? Where you have, so map is a function that takes a function and will apply that function that it's given to every element of a collection. However, if you do a map of a function over a collection, that produces another collection. So then if you call map again with another function on that new collection, it'll run through it again, and then you keep doing that forever. And then you can call reduce at the end and boil it all down to a single value, the infamous map reduce thing. You can fuse, if the functions that you're passing to your map functions are all pure, you can fuse them all into one function and call map over the first collection and not generate any intermediate data structures. So you can optimize that down to to just one iteration over your collection. And that happens automatically. Yeah?
This seems, if I understand everything that you presented, this seems like it would be very applicable to like hard real-time applications too, because you don't, so normally functional languages are hard to apply in hard real-time because garbage collected, overhead, and so on.
Mm-hmm.
But this seems like all of that, it just drops out, so then you actually should be able to do like safety critical applications in hard real-time with this?
I would think so. Some of the problems in something like that is getting the guaranteed, because everything's happening in parallel, you can't know that you're going to react to an event within a fixed time window. Because there may be other work in the graph that will come ahead of it. So you would need to have some mechanism for prioritizing certain reductions that you're handling. You want to be, this is hard real time. That would be doable, I'm sure. But I don't know that the just pure HVM would do it.
The determinism, the time determinism will be lost, I think.
I think so, yes. So optimizations happen automatically. There's no optimization pass. There's no minus 03 to get it optimized. So when I told you about lambdas sharing bodies, and this is what hooked me on this, was he showed some, a long time, this is like a year ago, some code in HVML and the exact same code in OCaml and Haskell, and the performance graph of the OCaml and the Haskell just went exponential. And his performance on his programs stayed constant. I was just like, that's freaking amazing. I don't know what this program's doing, I don't care. I'm just like a total sucker for that kind of graph. And it's in those cases, it wasn't practical stuff. It was like doing bitwise arithmetic on Scott encoded binary strings. So you'd never do that in real life. But just the fact that that existed, I was like, man, I wonder what else will happen. What else you can do. And I, in vain, tried to apply that in some various ways and failed miserably. But it was still cool. Okay, so here's the really mind-bending stuff. There is no program stack. You don't call subroutines. There are no subroutines. There is no function call. It's just graph reduction. And so there is no stack. It's always amused me how we have wars over whatever the current argument is. Way back in the beginning, they argued over including a stack pointer register in machines. And the old guard was like, nobody's ever going to write software that's reentrant that you call subroutines. That's a stupid way to do programming. And you're going to burn a whole register just for that? Are you crazy? They're just violently back and forth. And finally, the hardware went out and everybody loved it. And well, now we're getting rid of the program stack again. We're getting rid of the hardware stack. So, of course, I'm talking if you actually implement these ideas in silicon. But regardless, at least I think, I'm so ingrained with the idea of a program stack. When I look at code, I'm just instantly, automatically, at an instinctive level, looking for the call tree. What function gets called when, how it returns, that goes away. And so if this catches on, we're going to have to totally rethink how we look at programs. Debugging is much different. You can't use a debugger. There is no stepping through your program. You can't stop at any point and look at the state of the program. You can't examine your registers, because your registers don't correspond to anything.
Could you not look at the state of the graph?
You could, but the graph is also going to be massive.
Oh, it's going to be enormous.
It's like looking at the state of your entire RAM and trying to
Yeah, okay.
trying to figure out what's going on. And oh, by the way, you can't even do printf debugging because the order statements happen in is undetermined. Backup on these optimizations happen automatically. A lot of the optimizations can happen at compile time. Like you write your program, it gets compiled into the graph structure, then that graph can be reduced down at compile time to the point where it's only waiting, it's totally reduced. It's only waiting for input. And so if you have a printf statement in your function somewhere, and the string it's like a string literal, that might execute at compile time. And you never see it. I mean, you never see it at runtime because it's already gone. And so what does the executed program even mean? So just mind-boggling ideas, things that just, yeah.
In this model, where does data fit in? Is the data encoded into the graph that you're computing over, or is there some other expectation here for how data lives in the system? Is encoded?
So you can encode, and in fact they have, and what they're going to release, they have constructors and destructors of data types in the language that compiles into the graph. And so like a list gets composed into the graph. And so when you come along and do a map on the list, then it automatically goes out and tries to do all of the map operations in parallel. Now, you can have, and this is one of my pet projects that I want to add to it, is adding native collections, like immutable maps, hash maps, or immutable vectors and stuff. I don't know if that's going to be valuable or not, but the data does get encoded using like Scott encoding or.
Oh, so does that mean that the size of the graph is connected to the size of the data you're processing?
Could be.
Is there any guarantee on the relationship between the representation of the graph and the type of data you're representing? So like, if I'm imagining a perverse state, if there's a certain type of data that you're working with, you maybe are reducing this graph really quickly, but if the data is encoded into that graph and you're having to operate over that graph as a way of working with the data, that might mean that you have extremely massive graphs, and maybe the efficiency isn't actually there simply because the encoding is adding like exponential growth factors on the way your data is encoded.
Mm-hmm.
So is there any guarantees on like the efficiency of the data encoding and how much work you have to do to operate per element on a given piece of data?
Yes, the guarantee is that it will be optimal. And I mean, seriously, that is.
So like they can guarantee, for instance, if you're doing a bit mask on the GPU over a given set of stuff, that the equivalent operation for masking data will be flops optimal and memory bound or memory optimal with respect to like if you just implemented in the raw hardware.
Yeah. I mean, the book that I got, that a lot of these ideas come from, is the optimal implementation of functional programming languages. And I mean, the guarantee is it is optimal. Now, the problem has been how to decide between those two operators that I mentioned earlier, how to collect garbage, because some of the strategies for deciding generates lots of garbage nodes, and then those become disconnected from the graph. And so how do you collect the garbage? This guy, Victor, found a way to do that. And it's cool. It's really cool. Uses the affine Lambda Calculus, I think. You have another question?
Sort of a carry on. What's the definition of optimal? Like how are we? No, I like to play the skeptic a little bit. Like
Sure.
there's no doubt I really think this is cool.
Yeah.
But I'm imagining how is there a way to encode a graph representation of a bit mask on the GPU that will apply a bit, or let's say a scan or something, as
Okay, so in the case where there's hardware built to handle a specific case, this is not going to be as optimal as that hardware. It's going to be optimal in like a theoretical sense of the number of operations you do. But like if you can implement integers using church numbers, and you can do additions of church numbers, with Lambda Calculus. That's obviously not going to be nearly as efficient as just slamming two integers together in the CPU. So in that case, it's not going to be optimal in terms of like execution speed given a particular hardware. However, if you implemented this in hardware, and that's something Victor has talked about, because the silicon would actually be very simple. There's just a handful of actual things you do in silicon. Then that would be faster.
So like if your hardware encoded the integers instead of in registers, say, or something like that, encoded it using this graph thing in their memory representation, you had some hardware protection strategy for this, it would be as efficient as the current CUDA architectures or the current NVIDIA architectures or the Intel architectures for addition.
I may be speaking out of line, but I believe so, yes.
That's a bold claim.
Yeah. So I want to qualify. I don't really know, but I think so. Yeah.
I wanted to make sure I understood. So, generally, when you write in a Lambda language, right, it looks like you write a map or reduction recursively. What that looks like in a normal compiler is you just introduce serial data dependencies. Am I to understand that this will actually remove those serial data dependencies so that my map will actually be discovered to be possible in parallel?
Yeah. For a map function,
Right.
that
So obviously a full generally really does introduce serial dependencies.
and so like if you're doing a reduce where it accumulates a value going down, and those are really truly are serial dependent,
Right. Exactly.
then that will be serially dependent. But there might be parts of that problem that can be done in parallel. Yeah. Actually, go back to you.
Yeah, so I wanted to get into the optimality a little bit more. So I hear optimal, I think, I'm assuming that means like the number of graph reductions.
Yes.
So my follow-up question is like, what is the work in determining the next graph reduction? Like how much, like what is the complexity of actually, I'm curious, like is the complexity being shunted into like determining the next graph operation?
No. The way it works, last I looked at the rest code, is there's a list of active pairs that could be reduced. And it's in a list, and then all your threads steal off of that list, stack, list, queue, whatever. And so it will take a pair off, it will apply the combinator to it, and if that combinator produces another active pair, it will stick that back onto the list.
Okay, so it's effectively no work in deciding the next course of action.
Right.
You're not globally searching graph for
Exactly. You start with a list of pairs, and then that just keeps getting updated as you.
That's how he's able to work on multiple different parts of the graph in parallel.
Yep.
Right. So to carry on Ed's discussion, like with a fold or something like that, if you have a scan, there's most ways that code would represent a scan involves embedding in linear dependency in the execution of the scan. But with associative, some kind of associative operation that can perform the scan over, there's parallelism to be had there, but it's not encoded in the execution implied by the code. You have to rewrite your algorithm. Will this discover mathematical properties like that and take advantage of those, or is it limited to the mathematical properties encoded in this source code already?
It will discover them.
So it'll be able to turn a linear scan into a tree reduction scan.
If that's possible.
How would it know that plus is associative in that case?
How
does it discover associativity of a mathematical operation?
Magic. No, you can kind of think of it as the pair, like there will be a application node that's going to call plus. And in the graph, it's going to have a chain of two parameters so that it can operate on it. So as soon as both of those parameters become available, then that operation, that application gets put on the stack to be of a operation be done.
But if it's an accumulator, right, it's written like an accumulator.
Mhm.
But it doesn't have to be written like an accumulator if you know that the operation is associative. But otherwise, it's going to be the execution stuff. It's still going to assume a linear dependency with the accumulator. How does it know to get rid of the accumulator and completely rewrite the code?
I'm going to have to, I'm not going to be able to explain that now. I'm pretty sure that it will. And maybe we can get together and talk about that.
If it can do that, I really want to see how.
Okay. There was some other over here. Oh, wait, back there.
I could have misunderstood this. So if I have my Python, it sounds like you're writing a Python that transpiles this
Mhm.
kind of a higher level. Does my Python have to be written free of side effects and functional in order to benefit this Lambda calculus?
I think that's to be determined. I think my guess is no. Because the side effecting functions will be like kind of captured as chunks of native code that get called when their parameters are available. And so then it'll like drop into just that machine language and execute that whenever it's possible.
And another question is, it makes sense, I think I'm following how this happens at compile time. Is there also stuff that's happening at runtime here?
Yeah. So it does the same stuff at compile time as it does at runtime.
Okay.
So it compiles, it takes your Python code, creates this big data structure. That's just a graph.
Yeah.
It has active pairs in it. We know what the active pairs are because they got marked during compilation. And so then it just starts attacking those active pairs and starts reducing them until all the active pairs are done. And there's no more being added to the list of work to be done. And then that's going to give you a graph data structure. That then is your compiled program. And so then when it starts up, it's like, give me a piece of input. All right, that piece of input then triggers an active pair to be created. So then that active pair gets reduced and generates more active pairs, and then your stuff starts executing. So, yeah.
So I want to try rephrasing a very earlier question. So the strict and lazy lambda calculus, when reduced, sometimes have different results. Because in the case of the strict lambda calculus, can't deal with like certain types of recursion, for example. So would this be equivalent to the lazy lambda calculus in that case, where like if I start throwing a y combinator and stuff, is it going to like produce useful values, or is it going to?
Yeah, so they have plans to do both a what is it? Lazy and no, not lazy and strict. Lazy and parallel versions of the machine, so that the lazy, and I'm way off into the weeds here, into the fog. So get on the Discord. By the way, get on the Discord, ask lots of questions, and follow Victor for really up-to-date stuff. But they postponed the lazy. So the lazy won't reduce all of the graph. It'll only work on pieces that it needs to do to get some stuff done. And here I'm waving. You see me waving my hands? This is me waving my hands. But they postponed the lazy form of the machine to get out the CUDA stuff. They felt the CUDA was more important than the lazy stuff. So, how are we doing on time? Okay.
So you show one of the transformations that basically you have like basically two same inputs and like you said it's magic between I don't know notation. How does that keep checking on the actual program? Does he just run both of this even both of this before?
No. No. What you do is, where you have those two triangle nodes, the two duplication nodes, you add a label to those two nodes. And so inside a Lambda body, for instance, the duplication nodes inside that body, at that level, would have the same label. And then as the process goes on, if two duplication nodes meet that have the same label, then you choose the annihilation. They came from the same place, so to speak, and so they annihilate each other. If they have different labels, then you do the duplication, where they duplicate each other. And the way of managing those labels and incrementing or decrementing them as they move in and out of the lambda bodies and stuff, that's a whole, me waving my hands again. And also, just so this point's clear, the way it stands now, it does not handle all forms of recursion. There are some, some expressions like where you clone a function body that then gets cloned again. You can't really do that. And the compiler will pick up on it and tell you, hey, you can't do this. You're going to have to rewrite this particular expression. So there are some limitations. And also, to get the 73 billion graph interactions on the CUDA, to do that, they had to limit it to 29-bit integers because they had to fit 232 words into a 64-word for the CUDA to operate efficiently. And it needs 3 bits for a label, and so you only have 29 bits for your integers. So there are restrictions that you have to live within to get the performance. But there are also other, there are benefits, of course, and then there will be ways to do more general stuff and take a hit on the performance, like use 64-bit integers, which means your CUDA performance is going to be abysmal or whatever. So.
So my brain is oozing out of my ears here. One of the things that really spooks me about this is that the compiler will evaluate or optimize out even I/O statements, like a printf for debugging or the like. Could you do something where you're executing you're calling something like this from a normal function, from a normal programming language that has, stack frames and all this other boring nonsense, and then arrange it such that you have this enormous ring of data that you want crunched through very, very quickly, and then have this thing say, okay, I crunched through all that, here's your result, now you can go back with your semantically understandable programming language. Is that reasonable? Is that approachable? Or?
So my comment, or anytime anybody asks me, can you do this? I'm like, with software, I'm like, well, heck, you can do anything if you're given enough time and money. So this is like cutting edge research. It has yet to be seen where this all is going. The HVM is like the first real world implementation that's practical for some problems. So stuff like that, if there's a need for it, I imagine somebody will figure it out.
Yeah.
They're not figuring it out yet that I know of.
How much control do you give up on the predictability of the behavior of the system at a hardware level when you're doing something like this? So I'm imagining, like, if you're trying to use this to run some programs on computer, how would I have any way to predict my shared memory bank conflicts in my memory accesses with a system like this, where there's a disconnect there? Or if I want very good control over my memory patterns or my memory allocation costs, right? How can I predict how much memory this is going to use? Especially if, say, the other thing is true, like an associative scan, it will discover another way to do the associative scan. What if I, for reasons, computational theory reasons, I need a particular order of execution for a particular thing within the query, or I want to use only so much space that I don't want extra temporary space allocated to this on the underlying system? Like, what am I giving up control-wise to have something like that?
So my funny answer is monads. But the real answer is
You're giving up monads, or?
no. You use monads to get those guarantees. But honestly, I don't know. And I don't know that anybody knows yet. This is like new and nobody knows what it's going to be, what it's going to do. And so there's a lot of things to be discovered. And that'd be one of them. Like, how do you do exactly what you're saying? And so somebody's going to have to figure it out.
Is this like anything, like any way related to like the Futurama projections, where you basically, because you have the compiler, you kind of parse them down in your program to like get it executable. Like, is it any way related to that? Or?
If I knew what that was, I'd answer the question. I don't know what that is, actually. The one thing that I'll kind of wrap up with, but I'll talk as long as I got time, is our language. If this takes off, our languages have to change. And I think the way it's going is dependent type languages. We will have to prove our programs are correct before we compile them and run them in this environment. That's just my guess. I could very well probably am wrong, but yeah.
How is this all preliminary for computations with models strictly linear data flow? Imagine like a hash function or something. Is there any preliminary numbers for like how much slower this is?
Not that I know of.
I would expect there to be some cost
Yeah.
doing this reduction versus just doing a hash function.
Yeah, I don't know. Don't know. All right, well, I think we're about out of time. Sure. Well, hit me up, ask me anything afterwards. I'll probably say, heck if I know. Get on Discord and ask. But I'm happy to answer anything I can, and love talking about this stuff, because it has really renewed my interest in the industry. Because I was literally thinking about going to work in a big box store, just because I'm tired of programming. So I'll catch you afterwards, Aaron. So that's it. Thanks.
Thank you.